Discussion of the scaling law. But before that, let's, as usual, try to start from the review of what we are trying to do. Okay, so wait a second, why it is doing that? Okay, all right. Okay, so basically, what we are trying to do is to understand the critical phenomena. And especially, there are several important parameters, basically the critical exponents, okay, that basically describe what's going on nearby the critical points. And those critical point exponents include alpha. I'll just write it down so you have a rough understanding about what is going on. And beta is basically something like magnetization, and it will grow in some kind of power law when we are nearby the critical temperature. And CV is the susceptibility heat, and it basically diverges as we are closing the critical temperature. And we have gamma, which is how the susceptibility goes when we are nearby the critical temperature. So delta, which is at when T equal to Tc, how the magnetization scale as a function of the external field. Maybe I should use little h to avoid confusion about the Hamiltonian. And eta, which is related to the Green's function or the correlation function in K space at exactly the transition temperature goes like k to the power of -2 plus eta. And of course, the other important behavior of the critical system is how the correlation length C goes as the temperature is nearby the critical temperature. Okay, so so if we try to zoom out and try to think about what we are doing, basically at the previous maybe last 2 lectures, we are trying to check what are the possible values of the critical exponents. Okay, so in our homework, we also did some calculation about a simple model where we are able to check the results analytically, and we found basically the homework problem or the previous example are basically the mean field theory results, and we will have some sets of critical exponents. For example, we found alpha equal to 0 and beta equal to 1/2, etc. And there are tons of them. Okay, so this is the possible one possibility of the critical exponents. And then what we did is that we said that maybe we can try to think about the problem from a different perspective, from the very simple dimension analysis, because we know the physical quantity has to have the right units. Okay, so if you put that into your consideration, you found that basically, let me write down the physical observables must have the right unit. Okay, this is a very important constraint for, no matter where you are doing experiments or you are doing theory. Okay, so using this constraint, what we found is that simply using dimension analysis, they only allowed critical exponents or the mean field values. Okay, so why do we went through that? Because we want to make sure that no matter what kind of theory we are trying to explain, basically it needs to satisfy the simple dimension analysis. Okay. However, the trouble that we are facing is experimentally the critical exponents deviate from the mean field results. Okay, so then we have a trouble that, wait a second, if dimension analysis tells us that the only possibility is that we need to get the mean field results, then it means that what experimentally measured must be something that is beyond the simple dimensional analysis. Okay, so the question is how to reconcile or how to go beyond the mean field theory. Okay, so we have several proposals that we first notice the first thing. The mean field theory, basically it drops the fluctuation. Okay, so a simple idea is that, maybe it is because mean field theory dropped this fluctuation. So once we put back the fluctuation, maybe we can cure the problem such that we can have some theoretical understanding about why the critical exponent is beyond the mean field theory and explain the experimentally observed data. Okay, so that's basically the idea. So what we did is that we said maybe we can approximate the fluctuation. Okay, and the simplest approximation is basically the Gaussian approximation. Okay, and using the Gaussian fluctuation, what we found is that indeed we changed some of the values, including the specific heat behavior. However, it does not modify the other critical exponents. So we are realizing that maybe including Gaussian fluctuation is not enough. So we said that maybe we need to go beyond Gaussian approximation. Okay, so in order to go beyond Gaussian approximation, we said that maybe if we just want to solve the problem exactly, it is too complicated. So we said that maybe we can develop some kind of perturbation theory. Okay, then we spend some time to formulate our theory using the dimensionless parameters such that it looks like this, that the partition function is essentially the functional integral of some dimensionless order parameter field with the effective Hamiltonian, which is a functional of the order parameter field phi. And this actually effective of phi essentially is this d-space integral of the gradient phi square plus the quadratic term and the quartic term. And the argument is that maybe we can consider this quartic term to be a small object such that we can develop our perturbation theory in terms of powers of this U naught, okay? But the unfortunate thing is that we realize that this U naught actually will diverge when the reduced temperature goes to 0. And that means that no matter what kind of perturbation series you are generating by consider this U naught as a small parameter, eventually you got a perturbative series with every term diverge when t is approaching 0. Okay? So it seems like naive perturbation theory is not going to help us to understand what this critical phenomena really is. So that's why we need to develop something which is what we call the renormalization group theory. Okay. So before we go to the renormalization group theory, we introduce the idea of scaling theories. So what scaling theory is telling us is that you might have a bunch of critical exponents, but the critical exponents are not independent. And they need to satisfy several relations. The first relation is beta delta equal to beta plus gamma. And the second equation is alpha plus 2 beta plus gamma equal to 2. And the third equation is 2 minus alpha equal to mu d. And the fourth equation is gamma divided by mu equal to 2 minus eta. Okay? So the question is why these critical exponents need to satisfy this relation. So in our last lecture, we introduced the Whedon scaling law. Okay. What we then found is that magnetization can be at reduced temperature, and the external field can be expressed using this type of functional form. Okay, when temperature is greater than the critical temperature, or when temperature is smaller than the critical temperature. And in our last lecture, we basically take this functional form, and you can easily try to do some calculation about the susceptibility and the magnetization. Then you can find a relation such that you can basically show the first equation holds. Okay. So now we realize that basically in order to construct these relations between these critical exponents, we are essentially postulate some functional form that is based on some dimensionless parameters of our problems. Okay, and from there we argue that there should be some relation between these critical exponents. So now we are trying to go a little bit further. We can also try to write down the scaling hypothesis for the singular part of the free energy. Okay. So what do we mean by that? So in principle, we have some free energy. Now we only care about the singular part because that's the part that we will observe the non-trivial power law or some scaling behavior. And basically, we will assume that the singular part of the free energy will look like this. Okay, so here, this ff is just a function that is regular when h is sent to 0. Okay, so at this point, I'll just pause here and ask a question. Why we want to guess the singular part of the free energy has this form. Okay, so the hint is by definition how the susceptibility heat diverges when we are nearby the critical temperature is that it looks like this. That's by definition. Like we don't know what is alpha, but the definition of alpha is that your susceptibility heat basically diverges in some power law behavior. So the question I'm trying to ask is why I can get this in relation by knowing this definition. 好，接下来就是我们的简单讨论时间，就是我们上一堂课基本上做的事情是假设 V 人猜出了这个奇怪的函数形式 ，OK， 然后我们用这个函数形式呢去建立critical exponent beta、delta 和伽马之间的关系，这是我们上一堂课在做的推导 ，OK。那推导不是到非常困难，那如果大家回去看那个笔记，基本上就可以一步一步的，就是重做出这个行为这样。好，那我们可以用类似的精神哦，那我们去猜猜看，如果今天我们也要让我们的 free energy 有一些 scaling 的行为，我们应该怎么去猜它？那在Golden Field 教科书里面，它基本上就是假设它会长这个样子，就是我们现在荧幕上写的这个样子 ，OK。那我想问的问题就是，为什么我们可以这样猜，或者是为什么这样猜是一个合理的就是操作，不是说我们好像就是完全没有任何 physical argument 这样 ，OK？ 那大家有没有什么想法吗？为什么我们要这样猜？然后那个提示是，我们知道 specific heat 在 critical temperature 的时候会爆掉 ，OK？ 然后它爆掉的方法呢，是你会是你的 reduced temperature 的某一种 power law 爆掉，然后那个 power law 的那个指数 power 是多少，就那个 alpha 基本上就是根据你的实验上 CV 怎么爆掉去量出来的，所以我们其实不知道 alpha 是多少 ，OK？Mean field theory 可以给你某一些 alpha， 但是不一样的系统，你的 alpha 的值可能不一样。那从这边你可以猜出来为什么你的 free energy 应该长这个样子嘛？这是主要想要问的问题。然后有一些奇怪的假设，就是这个 FF， 就是后面这个函数呢，其实它是一个蛮正常的函数。如果你把 H 趋近0的时候，它是不会爆掉或干嘛，它就是可能就是给你一个常数之类的。 有这其实没有很难，但是就是还是希望就是跟大家有点互动这样。OK， 好，那今天就来进入讨论阶段。那我们从左边开始好了。所以第一位是陈同学，你有什么想法？你觉得为什么要这样猜吗？好，没关系。那下一位是，我有点忘记，你是黄同学 ，OK， 好，黄同学，你觉得为什么我们要这样猜呢？你有什么想法吗？好，你也想一下。好，再下一位是，这位应该是陈同学吧？是吗？是你是陈同学吗？还是我记错？哦，好，陈同学，你想想，你有什么想法？你觉得为什么要这样猜呢？嗯，哦，OK，所以陈同学说，我们知道 CV 跟温度有一些关系，它大概是什么 free energy 为个2次之类的这种东西之类的。然后我们的方程式可能是错的，但是不管，反正就是可能类似这种东西这样。就是我们可以查出方程式以后，我们就可以照做，然后就可以推出来它是可能是这个关系。所以说不定我们就可以猜出来。OK，好，那后面那位是石同学吗？是不是？你是我忘记你的姓了，不好意思。哦，林同学，好，林同学，你觉得呢？你也不确定，不是很确定为什么要这样猜。好，那下一位林同学，你跟陈同学的想法一样，觉得这个是一个好的做法，这样。好，那呃，其实，我觉得就是那个陈同学跟林同学的想法基本上是对的哦，就是基本上，我可以想就是今天我们要连接的东西是一个东西叫 specific key，然后我们知道的东西是 free energy，然后我们也知道 specific key 和 free energy 有某种程度的关系，所以说之所以它会被假设成这个样子，基本上就是因为这个方程式。你可以直接把这个方程式拿起来，就是做温度做2次微分，然后再把 T 乘回去，就是你真的做这个微分做过以后，你就会发现的确这里应该要给它2减阿尔法次方。OK， 那剩下的部分呢，我们为什么要这样做，就不是那么明确。OK， 但是我们知道一件事情是，这个关系就这个关系，我们在定义的时候基本上假设是外场是0。对吧？也就是说，这个函数我不知道它的真正的形式是长什么样，不管。但是在 h 趋近0的时候，它的行为应该要是给我这种 CV 的话，那表示后面这个可能是很复杂的函数，它在你把 h 趋近于0的时候，它的行为不能是很奇怪的，它必须要是很正常的行为，这样子才不会干扰到你前面猜出来的这个2减阿尔法次方。这也是为什么你在后面这里要加一些单数，就是这个 FF 不是随便的东西。你希望你把 h 趋近于0的时候，这个 FF 是在做一些很 smooth 的事情，要不然它变成一个常数啊，要不然它变成就是一个有上界的东西或干嘛的。OK， 所以这是就是大概在猜测。OK， 那在这个阶段，大家可能会觉得说很奇怪，就是我们为什么要用这一种有点像是猜答案的方式在前进哦？主要原因就是因为基本上这是实验量到的东西。其实我们现在有点像是重新复制我们以前在80年代还不知道normalization group 是什么的情况下，那你会面对一个未知的问题的时候，身为一个想要发展理论的人，最简单的也不是最简单，就是最常见的方法就是我们试着先去凑答案。OK， 那凑答案有的时候是有它的极限在嘛，你可能可以凑出大概的样子，但你不知道怎么解释。OK， 那现在这个 scaling hypothesis 是比较像是这样，我们试着要去凑一些实验上观察到的东西。 但是我们现在其实并没有一个很好的解释，为什么我们凑出来的样子，它在实际有一个理论真的可以支持，就是这个凑出来的样子是正确的。但是我们先不管那个后面的理论是什么，我们先试试看凑答案它会长什么样。OK， 好，那 OK， so now I think we have a rough understanding how this equation is guessed. Okay, so if we somehow guess the functional form of the free energy satisfy this relation, we basically know the behavior of free energy nearby the critical temperature. Okay, so the next question is, what are the other physical observables that you can derive from this free energy? Okay, so a very naive expectation is that we know magnetization can be derived by taking the derivative. This magnetization is like nearby Tc, just nearby the critical temperature, okay? And nearby the critical temperature, you can take the derivative of your free energy with respect to the external field, okay? So if you do that, what you have found is that you are taking derivative with respect to h, which is now living as an argument of a regular function, okay? So if you just do the chain rule, and what you will find is that this magnetization supposed to goes like t to the 2 minus alpha, but now because when you're taking derivative with respect to h, you will get some delta exponents in t, so you subtract delta, and now you get another first order derivative of your regular function as a function of the h divided by t to the power of delta, okay? So this is a very natural step once you guess what is the functional form of your free energy, okay? But now you might wonder, like, wait a second, I don't know what the hell this delta is, but let's just keep it there, okay? It is not something that you can derive from the phenomenological or like trying to guess the answer. Okay, so that's one thing. And another thing is that we also know from the definition that the magnetization goes like t to the power of beta. This is like the definition of the critical exponent beta, right? Then from here, what you're doing is that if you send h goes to 0, and you assume that the first derivative of this function f of f is regular. Also, this is like a guess or an assumption. Then what you will observe is that by comparing these exponents, the critical exponent beta is actually equal to 2 minus alpha minus delta. At this moment, we don't know what this delta is, but that's the relation between them, okay? So that's one clue. But we also know we have another clue. If I take the second order derivative of free energy, or taking the first order derivative of the magnetization with respect to external field H, then we got something like the susceptibility, and this should go like t to the 2 minus alpha minus 2 delta. And this 2 came from the fact that if you take the derivative of h, you will pop another vector t to the minus delta out. Okay, but now you have a second order derivative of this ff function, but let's just keep it there. And as usual, we assume that this thing is a regular function when you send the external field to 0. Okay, but there's another important definition related to the critical exponents of that is related to susceptibility. That's basically t to the minus gamma. Okay, so you got another relation that is basically 2 minus alpha minus 2 delta equal to minus gamma. Okay, then now you got two equations, and you don't want to have this delta because you don't know how to calculate it. So the easiest way to get rid of it is just, you just eliminate delta. And by shuffling those terms, you will get the relation alpha plus 2 beta plus gamma equals 2. That's the second relation for these critical exponents. Okay. So at this point, you already can see why these critical exponents are not independent, because this critical behavior somehow is all related to the critical behavior of your free energy. And the critical exponent, the critical behavior of your free energy actually relates a lot of physical observables, including magnetization, susceptibility. Because of that, those critical exponents are not completely independent with each other. And that's basically the spirit and why you get those relations. Okay? So, all right. So, I think at this moment, are there any questions for this relative simple derivation? Okay, so if not, I'm going to leave the last two relation as an exercise for you, that you can try to think about how to relate these things. And this derivation are basically covered in the textbook of Nigel Goldenfield's book, so you can try to read that. But the important point that I want to point out is that when we are arguing the form of 3 and 4, basically we are trying to construct the scaling hypothesis based on the dimension analysis. Okay, and what does that mean? It means that you are trying to guess the answer. Okay, and the observable that you are using to guess the answers are basically, you assume that basically the correlation length is the most important length scale nearby the critical point. Okay, so what you are trying to do is you try to form some dimensionless parameter using the correlation length and some of the microscopic length scale. This Li means some microscopic length scale. Okay, and using this information, you try to explore the possible form that relates to the critical exponents of like alpha and mu and eta. Okay, and I'm not going to do that here because in principle it should be relatively straightforward. And another reason I'm not doing that is because this is some kind of guessing process, so it is not guaranteed to work. But the point is that there's a way that you can try to construct this the relation between these critical exponents. And I'm trying to speed up and try to avoid the tri-error process to get this equation 3 and 4. And now I want to jump to the idea of the renormalization group. Theory. Okay? And so at this point, one of the very important things about renormalization group is that from the previous scaling argument that we just went through in the last lecture, and we tried to went through some of them in this lecture, you can notice that it is actually not very strict theory. to some extent, you are just trying to doing some kind of reverse engineer, and based on the phenomena, and you try to find some way to connect it with the possible theory. Okay, and it turns out that it is not still quite satisfactory to really understand where this non-trivial critical exponent came from, and that's the reason why we want to develop the understanding of the renormalization group theory. So let me try to went back a little bit and try to provide a bigger scope view about what we are trying to do. So we introduced the Landau theory, which is to some extent related to the mean field theory. So what Landau theory tells us is that when we try to change the temperature, we might have some phase 1, and there's a TC, and there might be another phase 2. So two important information that Landau theory tells us is that we can try to understand phase 1 and phase 2 according to how the order parameter transform under the symmetry of the system. Okay, that's one thing. And the other thing is that we notice that Landau theory basically assumes that fluctuation is small, so we can drop it. But unfortunately, we went through some argument describing the fact that nearby the critical region, that is nearby the TC, the fluctuation is actually large. So Landau theory is not a self-consistent theory. So at this point, we know that and the reason is basically fluctuation is important in some cases. Okay, so we cannot just naively treat what we derive using mean field theory as if the fluctuation is automatically considered very small. And as I already mentioned at the beginning of the lecture, that perturbation theory fails below a certain critical dimension. DC, and the critical dimension for 5-4 theory is 4 dimension, and we are living in a 3-dimensional space. So that means that in the phase transition in our physical dimension actually cannot be treated using the perturbation theory. So, so the scaling hypothesis kind of connect how these critical exponents are related to each other, but we did not really specify several questions. The first question is where they came from, and the second question is how to do a calculation for the critical exponents. Can we start from some microscopic model and really derive what are the corresponding alpha, beta, and other critical exponents? Okay. So scaling hypothesis tells us something, but the most important information that it tells us is that the critical exponents are not independent. Okay. In fact, only 2 of them are independent. Okay, so that's basically the most important things that we have learned until now. Okay, when we are trying to use the mean field theory to describe or to understand the critical behavior, then we will face this issue. And what renormalization group is trying to, or what renormalization group solve is that we actually can have a method to systematically calculate these critical exponents and understand where these critical exponents came from and how it deviates from the mean field prediction. Okay. So here are the important insight from the inventor of this idea, which is Leo Kadanoff. Okay. And the insight is not very trivial, but I'll just write it down and try to give some flavor about what is going on. So basically, what Kadanoff observed, or what Kadanoff have in mind, is a divergent correlation length implies that there's a relation, there's a relationship between first the coupling constant of a effective Hamiltonian and 2 the length scale over which the order parameter defined. Okay. So it is not trivial to identify these two relations, but we'll try to follow what Kadanoff proposed to do and try to see how, or try to understand how these two things are related. But a little bit unlucky for Kadanoff is that he basically formulated this kind of idea at the very beginning of the development of the renormalization group. But he did not really formulate a way to formulate a theory such that the idea can make some prediction. And it turns out that it is like how to do the calculation is invented by K.G. Wilson, the practical way. Okay, and also the not just how to calculate it, because once K.G. Wilson formulated the problem in a more precise way, the related interpretation about these physics are more clear after we formulate the problem in a more strict mathematical sense. So that also leads to the fact that K.G. Wilson got the Nobel Prize, but Leo Kadanoff did not get it. So that's a bit unfortunate for Kadanoff. But I think the insight given from Kadanoff is also should also be rewarded when we are trying to study the physics of renormalization group. And I think I went through an interview about Kadanoff, and the reporter asked Kadanoff a very critical question, like, what do you think you do not have? Like, what is the idea that you missed when you invent the initial idea of renormalization group, but Wilson had? And Kadanoff's answer is the concept of fixed point. So that means the idea of fixed point is very important when you are trying to understand what is the renormalization group. So we will also describe that part when we are discussing about the correct formulation of the renormalization group. But now we will just try to dive in the initial argument given by Kadanoff. So I think we will stop here and take a 10 minutes break, and we will continue the lecture after 10 minutes. And here is the homeworks. So if you have turned in your homeworks and you want to get them back, please come to take it, and see you after 10 minutes. Hey, 你交电子档那应该是被印出来，我猜。哎，等下你也是电子档？会不会没有？等下你是寄到哪里？你们是寄给我吗？
对啊。
哎，我好像没有收到哎，糟糕。没关系，那我再找找看好了。等下，这个是你的是不是？哦，这是你的。等一下，你姓什么？
用姓陈。
没有，好像没有看到你的。你是 email 给我吗？还是你是 email 给助教？好，那我再回去找找看。看起来好像这边没有你的，对不对？嗯。好，抱歉，那我再把它转寄给助教好了。好。
老师，我问一下，就是那我们之前好像没有特别强调，就是我们会去 study critical exponent。
对。
motivation 是要 identify 那个你的 Nosati class 吗？还是有其他原因？
哦，几个原因啊。第一个原因是第一是实验上观测到，然后实验上观测到麻烦的地方是，你可以看到这些 critical exponent， 但是是在完全不一样的系统。比方说你在磁性系统，你会看到一种 critical exponent， 然后你在液体系统，比方说相变，在什么水蒸气相变之类的地方，你也会看到一组 critical exponent。这两个系统看起来完全不一样，但somehow它们 critical exponent 是一样。这是第一件事情，就是你要去解释为什么这一类物理竟然会在两个我看起来完全不一样的系统，微观理论一定完全不一样，但是它却有同一组 critical exponent， 这是第一个挑战。第二个挑战是，你可能会想说，好，那我就用 mean field theory。那麻烦的地方是出现我们之前讲的那几件事。第一 ，mean field theory 给出来的值跟实验上量到不一样。那你有两种态度，一种态度是实验和理论本来就会差一点点，所以管你的这样。但是另外一种态度是，搞不好这是很重要的东西。那我觉得他们做这些 critical exponent 的人蛮厉害，就是他们嗅到了，就是这个看起来差一点点的东西，其实后面有很大的故事。要不然其实如果是我可能就会讲就差一点点10多万。对。那当然还有另外一件事情是，可能会比较重，就是 crucial， 就是如果你是理论学家，你就会注意到这件事，就是你如果做一般的 dimension analysis， 你没办法得到这个结论。就像我们之前做很简单的 dimension analysis， 然后我们发现糟糕了，就是 dimension analysis 告诉我的答案就是，除非你的 critical exponent 跟 mean field theory 一模一样，要不然你的 dimension analysis 告诉你那些 critical exponent 都是不合理的。那这问题就很大条啊，就是你做理论计算，结果你发现 dimension analysis 给你的答案跟实验上出来的东西不一样。那第一个问题就是，这一定是有什么东西 non-trivial is happening。OK， 或许这个是另外一个原因，为什么 即使你说那个差一点点，搞不好是实验跟理论有点误差，但是这个就真的你没办法 escape。如果 dimension analysis 给你两个字不一样，你真的没有办法解释它，所以你最好要有一个好的理论去解释它。所以他们就 jump in 去真的做这些分析，然后也 turns out 就是这是一个非常有趣的理论领域哦，就是发展了很多很有价值的统计力学的方法。就我们当然讲的部分都是比较well established， 然后比较不需要太 heavy 的一些计算，但是在计算这种 critical exponent， 其实我们后来也会讲一些简单的版本的计算法，像什么 cumulative expansion， 但其实为了计算这些 critical exponent， 在数值上他们有很多种不一样的方法，比方说你可以做 Monte Carlo， 然后你也可以做另外一种东西叫 series expansion， 就是级数展开的方式，然后是在 real space 去画图啊，然后你要叫电脑去帮你把这些图全部sum起来或干嘛的，反正就是有很多种招数可以帮助你去得到那些 critical exponent。那我们可能不会讲，但是只是跟大家讲说 ，OK， 这后面有一个大的概念是 RG。那为什么我一定会想要讲 RG 的原因，是因为这是一个如此重要的概念，就是如果你是做理论的，你一定要知道这个到底是什么东西，因为它和 effective theory 是紧密连接的，这是第一件事。那第二件事情是，如果你要 make sense of field theory， 你一定要有 randomization group 的概念，要不然你不会知道 field theory 是什么。然后另外一件事情是，通常 field theory 要教很多东西，所以很多时候你只会讲它怎么操作，但是它真正的物理意涵有的时候不是那么容易看得清楚，这样，所以我就选择讲非常缓慢的去考虑，就是这个东西的物理意涵大概是什么。那 hope 是有一些看起来很抽象的概念，如果你在场论写，其实你在统计力学看，你就会发现它的概念其实没有到那么不合理，其实它还蛮合理，就它背后有一套就是你可以了解，它不是什么黑盒子，就是你应该要相信所有以前的人讲的话，是你自己真的可以把它建构出来，就了解什么是 randomization group， 然后为什么这些 critical exponent 竟然可以不是 mean field 的值，然后你也没有办法用 fluctuation 的方式简单的 include 它，因为主要原因就是像我们讲嘛，就如果你做 scaling analysis， 你发现哦糟糕了，我那个 perturbation 在某些 dimension 的时候它是会爆掉的，所以我不管怎么展开，我每一项都一定是爆掉的。那你就遇到问题，你没办法解释它，至少用 perturbation 没办法解释。所以通常有一句话就是，任何东西你没办法用 perturbation 解释的，通常都是蛮重要的东西。就是如果你可以用 perturbation 解释，通常意思就是它跟你起始的状态没有差太多，你稍微变形一下它，你就可以理解发生什么事。它跟你的起始状态差很多，通常表示就是后面的物理通常都比较特别。对，所以这是为什么我会花很多时间在解释 RG 是什么这样。对，但是我不是很确定后来的东西，就后面的东西有一些像什么比较像什么 Bose-Einstein 或者是 fermion 的 interacting fermion 之类的东西，我觉得那个可能你在别的课程，比方说固态啊，或者是冷原子或多体物理，你可能会学到。但是比较仔细的去了解 RG， 我觉得可能只有在统计力学才会讲，所以我就比较 focus 在这一块。所以就花蛮多时间在讲 critical phenomena， 然后从最简单的 mean field， 因为我觉得 mean field 图像很重要，但somehow很多人都不知道 mean field 是什么，所以这让我觉得非常 surprise， 反正就是讲比较多这样，对，大概是这样。
所以这样的话，因为我其实常常听说，就是常常物理学家会研究什么，就是他们有看到什么 power law 就很感兴趣，所以原因大概就是这样嘛，就是要。
其中一个原因是 power law 通常就是会和self similarity 有一定程度的关系，但是为什么？就是你可以从 RG 里面可能会看到一些为什么会有这个结构这样。那当然还有另外一件事情是 ，power law 是没有 length scale 的东西，所以它不会有长度的概念，因为你可以把它 rescale， 然后你发现 power law 还是看起来一样。但 exponential 就是它有这个 intrinsic length scale， 因为你是 exponential 负的 r 除以 a 嘛，所以 a 一定是跟 r 是同一个 dimension。所以 exponential 的行为是本身是有一个 length scale 在的。那有 length scale 的东西比较正常，在自然界里面，因为我可能只能跟我隔壁的人讲话，那 length scale 就是 set by 我跟我隔壁的交互作用多强之类的。但是如果我只能跟我隔壁的人讲话，在一般的自然系统通常都是这样，就是短程的距离的交互作用。但是我只能跟我隔壁的距离讲话，但是讲一讲以后，好像变成说我们 沟通的距离可以到无穷长，比方说在 critical explosion 发生的事情，那这本身就是一个很不正常的现象，那表示你跟你的朋友和你朋友的朋友一定是在做某种很特别的群集行为，你才有办法把这个资讯传到好远好远的地方去。如果你们之间就是很一般的交互作用的话，通常这个资讯是 decay 得很快，所以有 power law 的东西通常会让大家觉得比较酷，就是 in the sense 是它是一个无穷距离的行为这样。那如果你是有 few body， 你当然绝对不可能做到这件事嘛，因为就是它有一个本质上的 length scale。但如果你是 many body， 然后你可以让这个行为跑出来的话，大家会觉得，哎，好像有一些 non-trivial 行为在，因为一定是大家一起在做一些怪怪的事。所以这也是一个 initiation 啊，就是为什么大家会对 many body physics 有一些兴趣，因为如果是 collective behavior， 意思就是你没办法借由分析一两个这种小家伙，你就知道他会有这种行为。你需要知道整体的，哦，原来他们大家一起在做某件事，你才会看到这个很酷的现象这样。所以这是我自己对 power law 的理解啊。但是，可能每个人有不一样对 power law 的理解，但对我来说，它就基本上是一个 signature of collective behavior。因为如果它没有 collective behavior 的地方，你不会看到这种怪怪的东西，对吧？对吧？OK， 好，大家等我一下，我去喝个水。好，欢迎大家继续讨论。
我先忘记了，那项里面有是写我也别忘了，我只记得它是就是要为自己的东西。这边我其实也没有很清楚，感觉它是从第一天，可是感觉是不同的。也是问题，就是想说它的边缘的趋势，后面是吗？后面的它为什么跳起来的就是为什么一开始是一减负啊，然后下一个是负啊？因为它是有两次在前，两次提在前。对，这个是也没有方面。哎，那个在讲那个后面有单位。
你说这个 F 啊？基本上你是希望它没有单位的。对，就应该说 H 和 T 都是没有单位的嘛。然后 F 通常是一个函数，然后你会希望就是一个函数我没有单位的东西也是没有单位，因为基本上你这个 free energy 也是尽量就把它弄正反面全成是。
那为什么我会觉得是一开始就是为什么像那样我会猜是1减阿尔法会是这个？
哦，你说这个啊？你是说这个东西吗？ 为什么是负阿尔法？原因是某种程度上这个 CV 是有点像是定义啊，就是为什么叫定义？就是你去看它的 specific hit 的行为，在二阶相变的时候，它都是尖的，就是爆掉那一种，就是它会慢慢变大。所以说，其实你会预期的事情是，T 越接近 TC 的时候，它要变大。如果今天你是正阿尔法，然后阿尔法是第一件事情，这个阿尔法是假设是正的，要不然你前面加正负号没有用。如果今天你的指数是正的，那意思是什么 ？T 趋近0的时候 ，CB 要趋近0，可是你实验上看到的是它要变大。所以如果你希望它变大，至少你是 power law 的话，它一定是再分母，就是 T 的某种 power 分之一这样。那如果再分母的话，它才 T 趋近0，它才有可能会爆掉。所以为什么就是这个阿尔法，就是它为什么是负的，然后阿尔法是一个大于0的数这样。对，那这个阿尔法值是多少，就看不一样的 fixed point， 它会有不一样的值这样。那我们现在在做 scaling hypothesis 的时候，我们不会去至少在现在我们做 scaling hypothesis， 我们不会去计算那个阿尔法是多少。但是我们现在得到的东西仅仅是这些 critical exponent 之间的关系是什么。那一旦它们有关系以后，我们就知道这些 critical exponent 不是完全独立的量。所以虽然我们看起来好像一大堆，在前面的时候有一大堆这种 critical exponent， 在这里我们有6个。但是呢，其实你可以证明或者是证实，其实有4个方程式是在建立它们之间的关系。所以如果你有6个变数，然后你有4个方程式，意思就是其实只有2个变数是独立的变数。所以说，你要去刻画一个 critical exponent， 其实你不需要知道所有的 critical，你要刻画一个 fixed point， 你不需要知道所有的 critical exponent， 你只要知道这6个里面其中2个。基本上你就可以得到其他的是什么，就是利用这些critical exponent 之间的关系就可以建构出来。那我没有特别去讲第3、第4，因为第3、第4是某种 dimension analysis， 你们应该就是可以在书上就是 follow 他们的 argument， 应该就可以得到。那前面2个其实也蛮简单的但是我只是想就是做一个大概的概念。最重要的东西，我想 demonstrate 就是你借由一些 scaling 的分，就是或者是一些dimensionless parameter 去建构一些你的系统的物理量，比方说你建构 free energy 的时候，其实你是在 impose 一些其他的量必须要有某一些行为，因为你可以从 free energy 得到 magnetization， 然后再得到 sensibility。那如果你知道这3个东西都和一些 critical exponent 有关系的话，那借由这个关联，就是 free energy 到 magnetization 的关联，你自然而然就会建立出这些 critical exponent 有哪些关系，这样，所以他们绝对不会是 independent， 所以他们有这个关系，所以虽然我们还没有计算出它的值是多少，但我们已经知道它有一些关系藏在他们背后，所以某种程度上也是简化问题，因为我们接下来要做的事情就是计算这些 critical exponent 是多少，但我们不需要所有的都计算，我们只要算出2个，基本上那个 critical exponent 就被限制住，大概是这样。Okay. Oh. So okay, so that's good. So let's try to continue. So as I mentioned, one of the very important thing about the RG is that the initial idea given by Kadanoff to some extent captured most of the essential physics. But the problem is that the real theory that's properly formulated is given by Professor K.G. Wilson. And after you formulate that, you can really do some useful calculation and to make some prediction. So what do I mean by can be calculated? What do I mean by that is basically the framework give us the possibility such that the relation between the coupling constants at different length scale I'll explain what different length scale means and a little bit later, but at this moment I'll just write down the statement. And what that means is that the renormalization group actually gives us some explanation about the possible critical exponents. At this moment, it's not clear, but I'll just say what it is. And once we know the idea of critical exponents, we can also realize that some of the property is important and some of the properties of the system is not important, so that the critical exponents will not be influenced by that. And that means that some of the microscopic detail of your model is not important, which means that you can have a lot of different microscopic models, and they all give you the same critical exponents, and they all belong to the same universality class. And since there's a good question during the break, that the question is, like, why do we start the discussion, or why do we get interested about the critical phenomena? Okay, because if we just try to think from the experimental point of view, we have some experimentalists, some of our friends, they measure some critical exponents that's different with the mean field prediction. So what? Maybe the experiment is not done properly, and no experiment is perfect, so there's always a discrepancy between the experiments and the theory. Why should we bother about that? Okay? So the argument is that there's something that's really amazing about the experimental measurement. The first thing is that you can measure the critical exponents in some system like magnetic system. You have a piece of magnet and just cool it down and measure the behavior nearby the critical temperature, okay? Then you got a set of parameters, or like a set of critical exponents that describe what is happening nearby this temperature according to your experimental frame one, okay? And another experimentalist who is like working in a completely different system. He's studying something, or he or she is studying something like a liquid, and how liquid transform into vapor, okay? So he or she is doing the experimental measurements, and on a different system, basically water and vapor, and measure the critical exponents, and their group got a different set of critical exponents. And it turns out that these two very different systems, one is the magnetic system and the other is the liquid vapor experiment, give you the same set of critical exponents. So that's already surprising one, that in a very different system, it turns out that you can measure the same critical exponents. So naively, we was expect there's something deep, or there's some not trivial connection between these two sets of different experiments. That's one thing. And the second thing is that from the theoretical point of view, as we have demonstrated previously, we can do some very simple dimension analysis that just try to consider the unit of the appropriate physical observable. And what we found is that we cannot use this dimension analysis to describe what we observe experimentally, because the dimension analysis tells us that the critical exponents must be some values, and the experiments basically measure something that deviates from that value, okay? So from the theoretical point of view, this is really bad, because it means that the naive unit analysis has some deep trouble. We need to modify our analysis. Then the question is, why should we do the corresponding modification such that we get the correct critical exponent? So that is not trivial. So basically, critical phenomena is amazing from both theoretical side. and experimental side, that we realized that to really describe this critical exponent, it is not easy. Okay, so that's one of the background motivation why renormalization group is important when we are trying to understand the critical phenomena. Okay, and it turns out the influence of renormalization group is much larger than just studying the critical exponents. That's also the reason why K.J. Wilson eventually get a Nobel Prize. Because when you are studying high energy physics or particle physics nowadays, the description of field theory is basically essential in this area. So at the very beginning of the development of the field theory, people faced the question like divergence in deprivation theory, okay? And there's no rationality about how to cure that until the idea of renormalization group is invented and people realize that what they are doing in the previous calculation seems like a mathematical trick, actually has a physical interpretation. And that also, helped field theory to establish his stage such that it becomes one of the most important language to understand fundamental physics. Okay, so in that sense, the concept of RG not only describe or understand the mystery of why critical phenomena has such a behavior, it also influenced the development of field theory and make it a very prosperous research field in the future. Okay, so that's like a very broad background why renormalization group study is very important. And today we are going to follow the history that you start from the very vague idea that okay, experimentally we measure this thing, and we have some discrepancy between the mean field theory and our understanding. Now we are trying to find a way to connect all this. So the idea that basically that we are going to follow is following the Kanonov's idea, and his idea basically will be based on two very important assumptions, and the example that we are going to use here is called the block spins model. And initially it is given by Kadanoff. And to some extent, this block spin model is invented because of Kadanoff's insight and the scaling law postulated by Whedon. Okay. So let's try to formulate the problem in more detail. So the first step is to consider a system let's call it omega of spins on a d-dimensional lattice. And hypercubic just means that it is a generalization of the cubic lattice in d dimension. And to be more precise, it is a hypercubic lattice with spacing A. Okay. So to make the story simpler, we will just consider to help us to imagine what's happening. during the class, basically you can consider the case when d equal to 2. A two-dimensional hypercubic lattice basically is a square lattice. So that's something that we are very familiar with. And the spacing between these lattices is basically just A. Okay? And on the vertex of this lattice, basically we have a bunch of spins sitting around. Okay? And I'll not draw every one of them, but you just remember that on the vertex of this square lattice, there's a spin. Okay, so it is now we should be quite familiar about this setting, and we know that when we are trying to form the partition function, one of the very important quantity is the beta times h omega, and h omega is basically the Hamiltonian of your system. So let's try to start with the Ising model, which is something that we are familiar with. And this angular bracket with ij just means that we only consider the spins that such that the I and j spins are nearest neighbor. So this term just means that you will only couple with the nearest neighbor, and j is basically the energy scale for this coupling. And we also consider external magnetic field can align the spins that we are interested in. Okay, so to make our analysis more easy, we will try to rename this minus beta j and minus beta h to be the dimensionless parameter k and h. So once we do that, the Hamiltonian times the inverse temperature beta, this is just 1 over kBt, will just be k times nearest neighbor coupling ij, SISJ, minus h times SI. Okay? So now we can try to study this model. And as we mentioned that we care about the free energy behavior nearby the critical temperature and the critical field. So we use and we also know that nearby these critical points, the free energy will have some singular behavior. And we basically are interested in how these singular parts behave nearby this critical point. So let's try to use Fs to denote the singular part. Of the free energy density. Since in our case we are discussing the lattice model, so the free energy density is basically the free energy per spin. Okay, and we are discussing the physics near Tc. Okay, so what does that mean? It means that the lattice spacing is actually much smaller than the correlation length. That's one thing that we know. And the idea of the block spin is that we are trying to do some kind of cross-graining, as we have done previously, that we try to choose a cross-grain size block L, such that the lattice constant is much smaller than L times the lattice spacing, and it is much smaller than the correlation length, because correlation length is always the biggest length scale nearby the critical temperature. Okay, so what we are trying to do is try to do some kind of cross-grain process. What that means is that imagine that maybe we have some kind of lattice at the very beginning, and this is A, and we try to choose a block of spins. Let me try to copy paste. Maybe there's some other repeated units. But what we're trying to do is we try to consider this is like the cross-grain block, where the length scale for this cross-grain block is L times A. Okay? And if you do this kind of cross-graining, what you expect to happen is that you got a new model where each red dot represent the cross-grained block, and these red dots, they again they live on the same square lattice. The same means that they are square lattice, but of course their distance might be different, because now this block is centered at some place, and the distance between these blocks, if I use the original length scale, it should be L times A. Okay. But anyway, that's basically just one process that basically we do the coarse graining. And after that, we effectively get a new Hamiltonian. Okay. So this coarse graining has a name. It's called the block spin transformation. And I will try to make this block spin transformation mathematically precise from now. So what is the block spin? Let me change the color. The first thing is that it contains L to the power of d spins. Okay, and the reason for that is also reasonable, because basically, even though in our picture we are drawing a 2D picture, but since the original problem is basically a d-dimensional hypercubic lattice, so what this block spin is doing is basically we are trying to do cross-graining on the scale such that the size of the block spin is L times d, which means that in d-dimensional space, we have a cube with volume L to the power of d spins. Okay, so this process is reasonable. And the second thing is that suppose we have some system that initially our system basically is defined by omega. So suppose we have n omega spins at the very beginning to begin with. So after we do the block spin transformation, basically we try to do the cross-graining, then the total number of block spins after we do the transformation will be n divided by LD. Okay, so this is also not difficult to understand, because you have initially n omega spins, and now you pack every LD spins into one block spins. Then eventually you have n omega divided by LD blocks for you to analyze. So now the question is, suppose for each block spin, we use some coordinate, that's say I, to represent the block spins. Represent the position of the block spins. Okay, so I is like the capital I, just to distinguish that block spin with the subscript I. Okay, so then I'm going to write down the definition of the block spin. It basically looks like this. So this SI means the block spin center at position I, and its value is defined to be 1 divided by ml bar, and I'll describe what ml bar is, times 1 divided by LD, times summation I belongs to this block, SI. And ml bar is basically 1 over LD for I belongs to the block spin, but with the average value of this. Okay. So what does that mean? It just means that this is just a normalization constant, such that when you do the average over the block spin, you only got two possible values. One is that either it is +1 because they have the same sign, or it is equal to -1. So to some extent, after you do this block spin transformation, you can really imagine this big block as a degrees of freedom that living on a new lattice, but now it still has the same binary variable that represent these degrees of freedom. Okay, so that's easy to see. So here is the assumption that Kadanoff is proposing. So here's the assumption one. Given by Kadanoff, that is the original spins will only interact with nearest neighbor spins and the external field. So the assumption is that after we do this block spin transformation, the block spins will also only interact with the nearest neighbor block spins and the external field. So that's the assumption. So let me try to write down the reasoning since the original. Okay, so the assumption is that the block spins now, after we do this cross-grain process, they will also interact with their nearest neighbor block spins and effective external field. So what does it mean? It just means that originally these little spins can only see their neighbors, okay? But now after you do the cross-graining, now you have a new degrees of freedom basically represented by these red dots. These red dots will also only couple with their nearest neighbors and the external field. So this is actually a very strong assumption that you will see why this is a very strong assumption and why at some point this may not be a true statement, but that's the assumption that at least at this moment it seems quite reasonable but not really justified. So we will try to assume it is so, and then we will ask what will go wrong if we try to validate that later. So if I try to write it down in a formal way, basically what we mean by that is that originally our Hamiltonian looks like this. Okay. Now, what we are trying to do is do the block spin transformation. And following the assumption 1, we will get another Hamiltonian, but now it's called omega prime because now the system is changed a little bit. And now we have another coupling constant K, but the format of the coupling is basically the same, that the block spin at center at I can only couple with the block spin center at J, but those J must be nearest neighbor to the I site. And you will have another effective external field, but now it is coupled with all the block spins center at I. Okay. So formally, if we try to write it down on the lattice model, it seems like that's what we are trying to say. But in this block spin model, basically the difference, there's another difference that the original model is defined for the lattice constant A. But after you do the block spin transformation, the lattice constant A prime now is L times A, because that you cross-grain your block spin by length scale LA. And as we already mentioned, that K will change into another coupling constant K prime according to our notation, and H will become another coupling constant H prime. Okay. So at this moment, I'll try to be specific because this K prime obviously will depends on how we cross-grain our system. If we choose a bigger block spin form, then this K prime will be different. So I'll try to give it a sub index L so that we know that the effective coupling and the effective field will be a function of how you do the cross-graining. However, we can try to think about another question. So to some extent, for this model, at certain coupling strength and at certain temperature, we can know there will be some kind of correlation length according to our parameter. So, so if we try to write down the correlation length, basically, in the first model, the correlation length, we can just say it is the correlation length can be measured using the lattice constant A, and we can use C1, which is a dimensionless number, to represent what is the physical correlation length. So this thing is dimensionless. Okay. So if we try to do this cross-graining, what does that mean? It means that the physical correlation length must be the same. But after we do the cross-graining, now we are trying to measure the physical correlation length, but using a different length scale, which is LA. So the dimensionless C for this scale LA will be assigned such that the physical correlation length must be invariant. Okay, so that leads to the fact that the dimensionless correlation length CL must be equal to the C1 divided by L. Okay. So to some extent, we always assume that L is greater than 1, which means that you are cross-graining, which means that you include more spins into a bigger block spin. Okay, so L is always considered to be greater than 1, and that implies CL will always be smaller than C1. Okay, so what does that mean? It means that now we are comparing two models, okay? One is the original model with little spins labeled by SI. And the other model is the still look like the lattice model, but now the degrees of freedom, now we call it S capital I. And they just live on a different lattice with the length scale that is a little bit different. One is with lattice space in A, and the other is with lattice space in LA. Okay? And other than those lattice spacing and the meaning of the microscopic degrees of freedom, basically the Hamiltonian that describe these two systems are completely identical, because that's a very strong assumption that given by Kadanov's assumption 1, right? So what we found is that if we try to measure the correlation length using different length scale, one is using the lattice constant A, and the other is using the lattice constant LA, we found the correlation length on the second model, which is CL, is smaller than C1. So what does that mean? It means that the Hamiltonian, after the cross-graining, this HL, is further away from the critical point than the original system. Let me just try to write it down. So basically, let me not try to use the curl L, let's try to use this HL. Let me try to be more specific. Let's call this thing HL. Okay, and let's just call this thing H0. Okay. No, let's call it H1 because it means that it is like using one lattice constant A to be the true lattice. Okay, so the point I'm trying to make is CL is smaller than C1 implies that HL must be further from the critical point. Than H1. So what does that mean? It means that the effective temperature TL is not equal to T1, and actually TL is greater than T1, which is greater than 0. Okay. So I think that makes sense, but I'll just put it right here and let you try to think about what we are doing. Because the idea is that first, the assumption one tells us that before you do the cross-graining and after the cross-graining, basically the Hamiltonian looks the same. The only difference is that the lattice spacing, one is A and the other is LA. Okay, and of course you have some couplings. Initial coupling is K and H, but after you do the cross-graining, you have something like KL and HL. So in principle, you can solve the correlation length as a function of KL and HL. Okay, and from the analysis that we are trying to build here is that when you are doing the scaling transformation, it tells us that after you do this block spin transformation, the corresponding correlation length, CL, will actually be smaller than the C1, which is the original correlation length measured by the lattice constant A. So you got a conclusion that if I try to apply how to calculate the correlation length in this cross-grained model, what I should get is the correlation length is going to be smaller than the correlation length of the original spin model. That's CL, which is the correlation length measured by the new lattice constant LA, will be smaller than the correlation length measured by A. So that also means that this model, in this cross-grained, after this cross-grained model, the effective temperature is actually further away from the critical temperature because the correlation length is shorter compared with the previous one. And because of that, we got this relation that TL is greater than T1, which means it is away from the critical temperature, and T1 is greater than 0. It's just by assumption that we are studying a system where correlation length is still finite, and we are able to do this kind of cross-graining. Okay, so that's basically the idea, and we will continue to think about what happened for the magnetic field, but it will be relatively straightforward because the idea is that now we have another term, which is a summation over the little spins, but now by definition, where SI, let me just reproduce it here. By definition, you can rewrite it as H times ML bar times L to the power of D times the summation over these block spins. Okay? Because if you sum over all these block spins, basically you sum over all the little spins. Then you got the same term as we have here. And when you are doing that summation, you will automatically get some additional factors. So these factors just kicks in to cancel the effect from this definition of the block spins. So basically that's what happened. And because of that, we can try to redefine these parameters as if it is the new external effective field. So what we got is this thing is basically the effective external field after we cross-grain our blocks with length scale L. And now we still have a bunch of block spins to interact with the external field. So that's basically how we get the effective coupling of HL from the initial microscopic model. Okay. So I think we will stop here and continue about the analysis of the free energy. But before we do that, I'll try to give you some flavor like why this RG is going to be useful. Because once you do this block spin, it means that your temperature is getting a little bit away from the critical temperature. And what does that mean? It means that your correlation length is actually getting shorter. And what that implies is that you have a better chance that you are entering a place where fluctuation is not too important. So you can develop some kind of perturbation theory away from the critical exponents, but eventually you can infer what is going to happen if you know the behavior of how your parameter changes as you do the scaling or like doing the block spins. So that's basically one of the ideas. But anyway, we'll stop here and take a 20 minutes break, and we'll continue at 2:30. Okay, so also there are some homeworks here, so if you want to grab your homework, please take it. Hello， 嗨。哦 ，T2 大于 T1 的 argument 怎么来的？就是我们注意到一件事情，就是我们在做某种程度的 block spin transformation 嘛，就是你本来是很多个密密麻麻的，这样，然后它变这样子 ，OK。然后我们又做了一个很强的假设，是你这样做完以后呢，我们期待就是假设它的 Hamiltonian 不会改变太多，它可能是长这个样子 ，OK。那我们的 assumption 是第一件事情，在这个 H1 的时候，对不对？我们知道 H 和 K 的值是多少，理论上我们就可以计算一个 correlation length。然后这个 correlation length 在这个 model 它一定是用 A 当做长度尺度在两侧，所以说我们量出来的话，它就是如果我用 A 去量它，它就是一个 dimensionless 的 C1 乘上一个 lattice constant A， 那个就是那个 correlation length 的长度。OK。那假设我们今天在做这个 cross grain 的时候呢，我们如果没有失去掉太多的物理的话，基本上我们得到的 correlation length of spins 应该还是差不多 more or less 一样。那怎么办呢？那就是表示说，你利用这个新的 K prime 和 H prime， 你应该也可以去计算出一个新的 correlation length， 但这个计算出来新的 correlation length 应该会是 measured by LA 这个长度尺度，因为这个 physical 的 length scale 是不会变的。OK， 那如果这样子的话，那表示你这个可 CL 和你的这个可 C1 它其实是有一个关系在，就是可 CL 会是可 C1 再除掉这个 L， 然后这个 L 是你怎么去做你的 cross grain 的大小。那什么意思？意思就是说，当 L 大于1，因为通常我们 L 一定大于1，我们选更多的 spin 进来，所以说你的可 CL 一定是比可 C1 还小的。那我们知道我们的 correlation length 基本上是 diverge as a function of T。什么负缪次方法，如果没记错，就是有一个 critical exponent 是缪。那这意思是什么？就是你越靠近 T， 它就越大。所以这个比较小，意思就是表示它越远离 T 系。因为如果你 T 趋近0，这个可惜就爆掉了。所以说你如果是比较小的那一个，那表示你比较没有那么爆掉，所以你就是离 critical point 是比较远的。那比 critical point 比较远的意思，就基本上就 imply 你的 model 在这个 cross grain 过后，用 L 的这个大小去 cross grain 过后的 effective 的 reduced temperature， 应该是比一开始这个 T1 就是这一个 model 的所在的reduced temperature 还要再大的地方。因为如果你比它小，那其实你应该要爆掉比它更严重，这个可 CL 应该要大于可 C1。但其实我们得到是反过来，也就是说它其实应该是温度是比较高一点的地方。大概的argument是这样。
这个总分是多少啊？
总分哦，我有点忘记了，应该要问。我记得每一题是5分，然后我们要看一下里面到底有几题。 我们
一个小题都是5个，每一个
对，所以应该是
5开头是几个？
就是这是多少47，可能是50或55，我其实不太确定，我可能回去还要再看一下。对。
那这边加0.5加1的意思是什么？
它应该是分很多，就是不一样的次数改吧，所以有时候是就是
就一个主角这样。
就是对，就主角改的，对吧？它可能有各扣几分啊，然后就是它有写在里面这样子，对。
那个期末的报告是说，你可以只是单纯介绍一个物理这样吗？
你可以介绍一个物理或主题或者什么东西的，就看你有兴趣什么。然后，可是你要寄给我，重点是下礼拜前你要寄给我。
怎么样寄给你？是要把档案什么东西的档案就寄给你？
不用，你可以告诉我主题是什么，然后你大概想要怎么讲。就是比方说你想要讲一个大主题，比方说我要讲我不知道，某个材料里面的什么现象之类的，那我可能会跟你讲说 ，OK， 这个现象还蛮 general 的，你就专注在讲这个现象就好。那个材料可能太多细节，大家不一定有兴趣，或者是我们不一定可以理解，那你就不一定要讲那部分。我可能会给你这种类型的 feedback， 所以你就比较知道你可能要怎么做。那或者是你跟我讲说你要做弦论，哦好，那我可能就跟你讲说这个太大了，就是你要做弦论可以，但是
你要做的
你要跟我对，因为你的报告时间只有20分钟加10分钟，所以你不可能把所有的 background 都做完。所以好，如果你真的要做弦论，你就要把它 narrow down，弦论的什么东西和统计力学有关。因为另外一个问题是我们这是统计学课嘛，你至少要找到一个方法，就是把这个跟统计学做有一些连接。
最好找的是宁泰，
对，就都可以，就是看你喜欢什么。你甚至也可以去找 social networking 啊 ，Facebook 怎么 connect 啊，这种 complex system 都有。那你如果对什么塞车有兴趣，你也可以做塞车的问题，这个也跟统计学有关。那或者你对非平衡有兴趣，然后你想知道就是什么 disease 怎么 spread 之类的这种的也可以，但是要有一个
都是可以从那种因为你有些图它是你看一些文章，它本来就已经把那种函数那个什么 figure 都画好了，是可以直接用，还是你要自己再画一个？
没有要求你们要做新的东西出来。就你可以有几种东西，就第一是你做 literature review， 就是以前人讲了什么，然后他们讲的东西有画一些图，你可以用，但是你要告诉我引用在哪里，你不能拿别人的图当做自己的图。OK， 这是第一件事，就是正确的引用你的资料。
在它下方是吗？
就是一般的报告，通常报告我们就是对你在 reference 那边引，就是你那个东西是什么东西这样。那我知道这个不是你自己做的，这个是你参考某一篇文章出来的。
就是报告的结尾就是说这些图是引用在哪就好了。
有很多种不一样引用方式啊，但通常我会是这个图这样子，对不对？然后我会解释一下这个图是什么意思，然后后面再放一个中括弧数字1、2、3。然后我就看那个1，我就知道这一个是，然后底下你要有一个 reference 的1、2、3、4、5，就是各个你参考的文章，然后上面写1，就是那个本文里面写1，我就知道你这个是从 reference 1里面引出来的图，像这样子，就是一个正式的学术报告的概念。但是你不需要有新东西，你不需要说什么，就是我要把这个东西重新自己 reproduce 出来。你如果可以做到，我觉得很欢迎。但是我不知道大家，因为现在大家都很忙，要做硕士班论文什么的，我不知道大家会不会有时间做这件事。
我就觉得时间
如果可以你就做啊，如果你不行，我觉得最重要的东西是逻辑概念，就是这张图告诉我什么事情，然后这件事情为什么和我报告的主题是有关系的，它为什么是重要的，要给我逻辑概念。然后基本上是用英文写，然后还有什么？还有就是题目就是。你如果给我太大，我会告诉你要做小一点。如果你给我太小的题目，我会跟你讲说你要再加哪些部分。如果你给我一个完全和统计学无关的东西，我就要跟你讲说你要试着去找一个比较和统计学有关的东西，大概就这样子。所以重点是下礼拜要寄相关的资讯给我，然后我才有办法回你们。要不然如果我没办法回你们，你们自己做，那可能就会变成 final 的 presentation 会很就是 fluctuation 会很大这样子，对。然后几个重点就是你们可以去看，就是我们之前的课程网页里面有一个简介或什么东西，我可以再把那个寄给大家，提醒大家说要做什么事情会比较reasonable 这样。那如果除非是你很在意自己的操作，因为有些人不喜欢做那个 literature review， 喜欢自己写 code，那没有问题，你也可以自己写 code。但是就是你如果不想要读 paper， 你就是自己写你喜欢的东西，那也是 OK。但是就是你要有足够的时间和动力。那如果你觉得你没有那么想要去实际的把这些东西 implement 出来，那你就可以就是针对一个你有兴趣的主题去了解它。
然后 implement 一个新的东西也是好玩，可是要有时间。
对，就是所以是觉得这是一个就是看你有兴趣到什么程度。
它的 code 都是有 code。
对啊，所以如果说你可以能够把一个主题或一个现象讲清楚，让大家一起学，我觉得这样就很 OK 了。就是没有说你一定要自己重复整个 reproduce 什么东西这样，但是不阻止你们 reproduce。如果这样讲，如果你有时间，我不会阻止你去做这件事。但是如果你没有到那么想要，就是因为大家都要毕业，每个人毕业的主题不太一样，你在赶毕业的时候还叫你去 reproduce 别人的 code， 基本上不可能的事情。所以我会觉得说，那你就做一个 literature review， 那重点是逻辑关系、动机，我为什么要做这个？为什么这个是重要？为什么这个有趣？然后试着把它讲清楚。然后如果大家可以从你的研究里面，就是这个 literature review 里面学到的东西，那大家就会比较高兴了，你就比较有高分的机会，大概是这样的概念。如果你讲到全场没有人听得懂，那也不是很好，所以那个分数可能就比较低。就是重点是你要怎么样，用物理的图像去解释，
还有英文练好一点。
对，还有英文练好一点，试着把物理图像讲清楚，逻辑关系交代清楚，去做一个类似，你知道物理学家之间的讨论的概念。就你喜欢跟什么样的物理学家讨论，你就试着往那个方向前进。你最不希望遇到就是一个嘴巴里面一直讲，但我听不懂他在讲什么的。所以最好的情况就是你试着了解内容以后，把它用简单的方式讲成就是大家听得懂。所以你要 set up 的 target 的 audience， 就是你的目标的受众大概是，
要把它当成他从来没有基础。
对，你可以想成就是他没有基础，他就是你的统计力学一的同学们，他们可能不一定知道那么多，但他有一些基本的统计学概念知道的，然后试着把这个主题用你知道的统计学概念把它解释给不是在做你这个方面的 literature search 的人说，为什么这个是这样，然后为什么它重要，大概是这样子。
还有那个上礼拜的那个笔记好像还没有在网络上看。
我没有上传吗？因为上礼拜是没有影片档啦，因为我没有录，但是我连笔记都没有，是不是？那可能是我忘记传了。好，那我上礼拜我再传一次，抱歉。对。对。
就是你都是跟完，把东西讲好，那我总是得弄一个，就没有东西会，就是 H 跟 A 自己设定，他跟他都是跟完。
等一下，我没有抓到你的问题。我一开始有这个，对不对？
我本来的 origin，
对，是这个 component， 对，
然后我不是跟完，
对，
然后我的长度跟progression length，
对。
那我总是可以在外面再找另一个 origin spin system， 然后4口跟选 length 是这个长度，然后 latest constant 是这个 LA， 然后correlation length 是除以那个 A 的，除以 L 的那个 scale， 就是
可以啊，
东西
可以，你可以做到这件事，但是我不知道你要做什么。
就这两个东西是一样的。
谁跟谁是一样的？
就是我 post 跟完之后的 spin system， 跟我没有自己另外设的，但是长度是不一样的 spin system， 这两个东西会表现是一样的。
会一样的是因为你的 correlation length 用新的长度尺度去量会是一样的。就比方说你这里的 correlation length 是可希望乘 A， 对不对？照你刚刚那个建构方式出来，你的 correlation length。physical 的 correlation length 会是可惜1乘上 LA， 对吧？OK， 所以说这两个系统虽然说就是它是同一个 model， 但是你调了这些参数以后，你得到的效果就是你的 correlation length， 就你还是可以这样做，但是你这样做之后得到的效果就是你得到一个新的 model， 然后它 correlation length measured in 他自己的 length scale 是不变的，这件事是做得到的。但是这边我们在做的事情比较不像是这样，我们这边做的事情有点像是，其实我们最终想要了解还是 H1， 对吧？就是我们最终要了解的是这个 Hamiltonian 的 partition function。那我们现在做这个 block spin transformation， 其实在做的事情是，我想要上我的 partition function， 但是我的上法不是以前那种上法，以前那种上法是我真的全部把它抵掉，就是整个上起来，那我得到严格解的，这是以前的做法。那以前我们为什么可以这样做？因为以前的系统没有，
反正就是我想要修的。
对，但其实我想要知道，其实最终的是这个东西的形。但我发现，就是我的确可以这样做，那我就做 block spin transformation 一点一点加，但是会有一些
然后指令的时候就是会比较，其实不太知道它那个机会远离那个 TC，就是它会比较真实、比较对的 crystal exponent。
哦，你是说这件事会不会导致我比较容易得到正确的 critical exponent？这是一个很好的问题，在现在这个阶段，其实你是看不出来的。
所以之后会。
对，你之后会看到，就是借由这种招数，你要怎么得到你的 critical exponent？ 但是这个 process 其实不是那么的 trivial， 就你还需要后面的一些 argument。但是其中一个比较重要的这个过程是，你会发现一件事情是，你在做这个 block spin transformation 的时候，你会改变你的 coupling constant as a function of 你怎么做的 block， 就是它是一个 function of L。所以其实主要的概念就是你的 coupling constant 会是一个随着你的 length scale 不一样的 coupling constant。然后真正酷的地方是，你的 critical exponent 其实是会和你的 coupling constant 怎么随着你的 block transformation 去改变，会连接到你的 critical exponent。所以现在看起来就是我们只是做一个 block spin transformation， 然后 k 变 KL， 但是 k 怎么变 KL 的，其实会告诉我们 critical exponent。这是他们找到的神奇的、酷炫的结论。
也在想 K 胖
啊？什么？
就是 K 胖到底是怎么变？因为你刚刚
我们现在没有讲这很清楚，所以现在你会看不出来。但是你现在可以看得出来是 K prime 和 H prime 都会变，但它变的方式是你会发现它会往比较 effectively temperature 比较低的地方，这是你现在可以看得出来，但是你还看不出来就是 K 怎么从 K 变成 K prime， 然后你也现在应该也还看不出来为什么 K 变 K prime 会 imply 就是你可以用这个资讯去抽出 critical exponent 是多少，这个现在我们还没有讲到。
我再确定一下，就是上一节是 anomalous 才会
我没有听到，
因为我上节上 anomalous。对。然后就是发现什么 anomalous 改变的都是一开始这样子跟 Q 一开始的 dimension Q 什么样，然后后来加入类似之后，就会变得
就有机会不一样。
它不一样是说，是跟实验还是？
这个部分我们其实没有讲它跟实验的关系，原因是因为我们第一件事情得到 mean field theory 只能是某一种 critical exponent， 对不对？然后我们第二件事情是发现这个 mean field theory 或者是 dimension analysis 用因次的方式去判断，其实有一些很强的假设，就是你因为这些假设而忽略掉系统还有另外一个重要的微观的 length scale， 有可能会出现。所以一旦你把这个微观的 length scale 放进来，你就会发现你的 critical exponent 可能会跟 mean field 结论不一样。所以重点就是这个微观的 length scale 是需要的去解释，就是critical exponent 为什么跟 mean field 值不一样。OK， 但是这个也帮助你一件事，就是实验上量到的 critical exponent 和 mean field 不一样是没有问题的。原因是因为有可能有一个理论，只要它可以展现出这种 length scale 怎么跑进来你的 dimension analysis， 你就有机会得到一切都自洽的理论，就是你的物理量有正确的 dimension， 然后你的 critical exponent 也和 mean 的值不一样，所以可以解释实验上的东西。但是在这些过程里面，我们并没有明确的告诉你怎么去计算这个不一样的 mean 不一样的 critical exponent 是什么。我们只有告诉你这里有这个结构，所以说你可以得到这个结论。那接下来我们要做的事情就是把 RG 搞清楚以后，你就知道你真的可以计算出那个不一样的 critical exponent。
所以一开始我们假设不一样的方式是用高镭射高面把你的时升加，
只有阿法会有点不太一样，就是它只会修正阿法的行为，但你会发现阿法还是联动。
要反开不会说成其他的。
你说
反那边再加进来。
没有 fluctuation 加进来的话，至少在高线 fluctuation， 因为我们有真的做计算，只有高线。
我讲过是 perturbation。
perturbation 为什么我们没有做？原因是因为我们试着要 develop perturbation， 对不对？然后我们发现做完 dimension analysis 以后，你发现 perturbation 的那个 phi 4次方前面的系数，随着你温度靠近 Tc， 它会爆掉。所以也就是说，如果你用那个东西当小量，本身就是不合理的，因为你靠近 Tc 的时候，每一个小量都爆掉。
所以意思是说，我们如果 perturbation 再加这边这个
RG
的话，就会得到
almost right， 就是 RG 会帮助你的事情是你的 perturbation series 的那个 U 有没有 small parameter， 其实它不会是真的爆掉的东西，它是某一个行为的东西。然后如果那个行为的东西是你可以控制的，你就可以用它来发展 perturbation theory。这个通常是在 field theory 发生的事情，就一旦你做normalization之后，事件可能不会真的爆掉，就有点somehow有 fixed 的 explosion， 或者是你在做其他计算的时候，你不需要真的去 exploit 这件事，就是你的 counting cost 会爆掉，但你还是可以得到 physical 你想要 measure 的东西。
前面 perturbation 可以算出这个 critical 还是没有？
其实没有，因为我们 critical exponent 我们只有做到。就是我们第一件事情 mean field 没有 fluctuation 嘛，然后下一步我们加入高线 fluctuation， 然后我们发现高线 fluctuation 会有一些效果，但它只会 correct alpha 的，就是 free energy 的行为，但是你 free energy 还是有降，所以 alpha 还是不会变差。所以你考虑高线 fluctuation 以后，你发现你 critical exponent 没变，
所以我们还是做
我们完全没有做 perturbation， 原因是因为 perturbation 你做 dimension analysis 以后，你发现它做不下去。因为每一项都爆掉，所以你没有办法得到有用的数据。所以告诉我们说 perturbation 至少naive的 perturbation theory 是不会 work 的，因为你每一项都爆掉，在 TC 的时候，所以你没办法得到有用的数据。所以下一个问题，所以我们有点好多条路都走不通这样。然后现在就变成说，我们这些不会 work 的东西呢，我们有没有办法找到别的方法去理解这个 critical exponent？ 那现象学上你可以去猜，因为如果我们知道就是微观的 length scale 会帮助你得到这个 critical exponent， 但是是 deviate from 就是跟一般的那个 naive 的 dimension analysis， 你可以去猜你的 free energy， 还有你去猜你的 magnetization 应该有什么 scaling， 这是为什么你去讲 scaling law 的行为。那一旦你知道 scaling law 行为是可能是长这样，那下一个问题就是有没有什么合理的理论可以告诉你的 free energy 和你的 magnetization 要长得像 scaling law 的这个行为。OK， 那我们就会讨论 RG， 因为从 RG 里面你就可以看得出来，就是为什么 free energy 和你的magnetization它要有这些 scaling law， 那你就把整个故事就都在一起了。然后下一步就是还有下一步就是 RG 只是告诉你说你怎么去算这个东西，但是你还记得我们很早以前讲那个 scaling law 的时候有讲 length scale 加一个小的 length scale， 你有可能会出现这些 critical exponent 的行为可以被修正嘛？所以说你可以在符合正确的 unit 下，你还是可以得到这些 critical exponent。但是我们并没有解释为什么这个东西会出现。那理论上，如果我们时间够的话，讲完 RG， 我们会去讲为什么 RG 会给你这个奇怪的东西。其实来源就是因为你的 你的 RG equation 它本身就有一些，就是由 dimensionless 的 parameter 去形成的。然后这些 dimensionless 的 parameter 在你进度，就你把其中一个趋近于无穷大之后，就当我们 correlation length set to 无穷大的时候，你要做一个更小心的分析，才可以得到那个正确的那个，就是趋近零的行为应该长什么样。然后如果你从那边的话，你就可以看出来，其实这种类型的 anomalous dimension 其实不需要 rely on 统计力学，但是它只要是一大堆就是 dimensionless 的 coupling， 在有一些竞争关系或者有一些 differential equation 它必须要满足的时候，它都有可能会出现。所以说 anomalous dimension 其实 in some sense 它是比或者是 RG 这个概念是比统计力学还要更宽广的。你可以在统计力学里面看到它，你可以在非平衡的统计力学里面看到它，你甚至可以在原子分子里面看到它。像 ephemeral physics 就完全和统计力学无关，它就解一个 three body 的 Schrödinger equation， 但是你却可以看到有奇怪的 self similarity 在这个系统。所以大概的概念是这样串起来的。后面那一块我不知道我有没有时间讲到，但是前面这一块是我们现在要努力前进的，就是到底发生是什么事，为什么 RG 会是 OK good。Okay, so we will continue, but before we continue, let me remind you another important thing, that we have a final project presentation. So please remember to send me the potential topic that you want to present during your final report. And once I receive your topic, I'll give you some suggestion. Like maybe the topic is too broad, you need to narrow down, otherwise we cannot, answer the question or have some reasonable understanding within 20 minutes. So that's possible. And another type of possible suggestion is that if you focus too narrowly on some specific topic that people might not have enough background, I will suggest you to focus on the phenomena, but try to broaden the phenomena a little bit further, such that it will be reasonable for everybody. Okay, so I will send out another email to remind you about the detail of the final project, and also I got the feedback that I haven't posted the note of the last week lecture. I will post it soon. I'm sorry that I forgot to do that. And another unfortunate thing is that I forgot to record the lecture of the last week. So we basically have no video recording. So please just take the note as a supplement material. And if you don't understand something about the lecture note, please just ask me after the lecture or send me an email and describe your question. And I'll try to answer them as much as possible. Okay, so let's see. So basically, what we are doing is starting from some Hamiltonian that we call H1, and we try to propose a possible way to do the cross-graining, basically doing this block spin transformation, and then we end up with the new Hamiltonian described by these block spins. But now these block spins have a different coupling constant according to how we do the block spin transformation. So the first thing is that maybe I should say that before we do the calculation, but now I think we can still see what we are trying to do. So of course, the target Hamiltonian that we are looking for is the original Hamiltonian, basically this H1 Hamiltonian, okay? So when we are doing cross-graining, in this way, basically we are summing up the degrees of freedom in some very systematic way, okay? So why do we do that? Because at the end, what we are trying to analyze is the partition function of our lattice model, right? And our lattice model is formed by a bunch of little spins. And in the past, like in statistical mechanics 1, what we have learned is that we just sum this partition function explicitly. And the reason is because there's no interaction, so you can really calculate the partition function in the analytic form. There's no problem. But now we are facing a more complicated system, and we also noticed that in order to describe this critical phenomena, mean field theory is not enough, so we did not using the mean field theory approach, which is that basically we reduce the problem into a single particle problem, so we can solve it again by brute forcefully summing over all the, every term in your partition function, okay? So this block spin transformation is trying to deliver a message that now you have a bunch of spins. You can try to use another way to analyze your problem. Basically, you sum up your partition function in a very regular pattern and sum your partition function bit by bit. So from the block spin transformation that we go from H1 to HL, what we are trying to do is we are trying to argue that maybe we can get or to understand the physics of our Hamiltonian by considering summing up the partition function in a fashion that the partition function can still be described by some kind of effective Hamiltonian of our original problem, okay? That's why we designed to sum the block spins in a very regular pattern. Because if you sum your spin in a very regular pattern, you have a better chance that you got your effective Hamiltonian that still looks like, your original problem. And to some extent, you have some understanding about your original problem, then you can apply that to the new effective Hamiltonian. Okay. So that's like the spirit why we are doing this summation. But let's continue and see what we can get from this quite formal operation. Okay, so another important thing is that after we do this summation, basically we got the effective coupling constant K prime and H prime. And as I mentioned, because now it depends on how we do the cross-graining, so instead of prime, I use KL and HL to represent the effective coupling after we do the block spin transformation, okay? But at this moment, we did not specify what exactly is this KL, because we just formally said that, oh, it is just a coupling constant. But in the later part, the important message is that how we start from K, and after doing some cross-graining, you got some effective coupling constant KL. How the couplings at different length scale are related actually will give you non-trivial information about your fixed point, and that will give you non-trivial correction to your critical exponents, okay? So this is something that is not very clear at this moment, but I'm just trying to give you a teaser that understand this process is not meaningless. It looks quite strange at this moment, but it is reasonable because we are trying to analyze our partition function, but we are now just summing up the partition function in a different order to some extent. It is not completely unreasonable. You can do that. And the second thing is that this is a valuable operation because we will discuss later that by doing this partial summation or cross-graining bit by bit, you can actually get a lot of information about how the critical exponents will be modified. Okay, so that's basically the motivation. So let's move on and see what we can get out from here. So, okay, so after this cross-graining, what we know is that basically we are getting to temperature or a reduced temperature that's a little bit further away from the critical temperature. So now, and we also know, oh, by the way, HL is easy to calculate. This is the one, we didn't know how the coupling K transform after we do the block spin transformation, but the effective magnetic field can be easily calculated because we know that almost from the definition of how the block spin is related to the little spin. Okay, so let's see. So the next information that we are able to derive from this seemingly quite artificial process is that the Hamiltonian at length scale L, and the Hamiltonian at the unit length scale of A, which is H1, basically has the same form. And the reason for that is, of course, it is come from the assumption 1 given by Kadanoff. Okay, so if they have the same form, we will expect the free energy that has the following relation. Because they have the same form, the free energy should also have the same form. So let's consider the singular part of the free energy as usual. And because this Fs is just the free energy per spin, so the total free energy is that we time the total number of spin, which is n omega, before we do the cross-graining, and that will be the free energy of our system. So now we are trying to say that, so we are trying to get the free energy of the new effective Hamiltonian. So what is happening is that because now we have a bunch of block spins, but the number of block spins will be fewer compared with the previous number of spins. By how much? Basically, the number of block spin is the total number of spin divided by L to the power of D. Okay, because every L to the power of D spins are packed into one gigantic block spin. Okay, so that's the number of block spins. And now you have the singular part of your free energy, but now with the effective reduced temperature that is defined at length scale L, and the effective external field that is defined at length scale L. Okay, so here the assumption one gives us is that the function Fs should be the same for different length scale. Okay, because the model is basically the same, the free energy will be the same, the only difference is the parameters. Okay, so that's how we get this relation, because we also mentioned that to some extent we are just trying to sum over our Cartesian function in a different manner. So the singular part of the free energy should still be the same. And this equality basically identify the singular part of the free energy for the model before we do the block spin transformation, and the model that after we do the block spin transformation. Okay. So this is cool, because if we understand this line of free energy, or the singular part of the free energy, what we got is the singular part of the free energy at the reduced temperature at the length scale L, and the external field at length scale L should be related to the original free energy density by this relation. Okay. And at this moment, we don't know how TL and T8 and L and HL changes during the transformation. To some extent, we know how HL transforms because it's relatively simple. It's right here. But we don't know how TL transforms. But that doesn't matter. We will see why this important information will be argued away to some extent. Okay. So at this point, it is basically what we can get by taking the assumption 1 given by Kadanoff. Okay? So we start right here, and the most important thing is that we don't know how TL is related to T. So the assumption 2 of Kadanoff basically try to address this question by, to some extent, quite brute force us. Assume that. So the idea he got is basically we are looking for power law behaviors. So why not assume TL is related to T by this type of relation? Okay, but at this moment you might think, wait a second, this is just too suspicious. How come you get this answer? But as I mentioned, this is at the very early stage of the theory. So to some extent, people are trying to get the possible structure by guessing and arguing how things should work. And the question is, okay, let's assume that this assumption 2 is correct. What are the advantages that we can get by taking this assumption literally? And we will see how it goes. Okay, so basically, assumption 1 tells us some relation, but we are kind of stuck at there. Then assumption 2 is basically helping us to proceed and try to get some results and see if it can be consistent with the observed behavior in the experiments. Okay, so this assumed answer, if we try to insert it into the free energy expression, okay. Basically, what we will get is by putting this inside here. Okay, so I'll just write it down. What you will get is the singular part of your free energy. It looks like this. Okay. And at this point, we should also remind ourselves that L is something that's greater than 1, but you can choose it freely. Okay, so you can cross-grain your system in using different L. And also, we know the absolute value of T is something that is quite small when we are studying the critical phenomena. So we can try to choose L according to the behavior of T. So if we choose L such that absolute value T times L to the power of YT is of order 1. Okay? Order 1 means that you can almost imagine that this thing is just 1. So just not to confuse everybody, let's just try to write it as 1. Okay? So if you choose your L in this way, what does that mean? It means that you can basically say L equal to absolute value of T times YT, 1 over YT. Did I get it correct? It should be a minus sign. Okay, that looks right. Okay, so if L looks like that, then you can try to plug that into your singular part of your free energy. Then what you will get is the singular part of your free energy as a function of T and H will look like absolute value of T times D divided by YT. And the function F, basically, now since L is chosen to be this particular value, this function will be with argument 1 and H times T to the power of minus, by the way, I think I make a mistake, it should be YH here. Minus YH divided by YT. Okay? So at this point, it seems like quite promising, because what we got is the singular part of the free energy has some power law dependence about the reduced temperature and some function that is formed by these dimensionless parameters. So if we try to look back about the scaling hypothesis that we derived some time ago, it basically looks pretty much like this guy. Okay? You have some dependence about the reduced temperature in some power law fashion, and you have some function that depends on some parameters of the reduced temperature and the reduced magnetic field. Okay, so let me just copy this line and try to make a comparison. Then I think that will be quite useful about what we are trying to do. So let's see, copy. Here, okay, paste. Let me try to erase everything to make sure it is clean. Okay. So if we compare these two, you will immediately get the conclusion that the previous delta that we assumed is actually YH divided by YT. And 2 minus alpha, which is the anomalous dimension alpha, is actually related to this D divided by YT. Okay? So that's it. So if you make this identification, basically you get the previously argued the scaling form of the free energy. And that's very promising because it means that if we take this assumption 1 and assumption 2 literally and believe it is true, there's a hope that we are able to get the corresponding free energy form that can connect to the experimentally measured stuff. Okay? But the question is, what is the value of this YH and YT? We don't know yet, but we will see how to calculate it a little bit later. But that's just like we are not doing something useless. We are getting there, but we just need to have some patience and get things more accurate. So, but at this moment, let me just try to emphasize that. But it is just the of delta and alpha. Okay, we didn't solve the problem yet, but at least this hint is quite promising. Okay, so now we can try to see another important thing, which is the correlation function. And we can try to ask how the correlation function behave if we try to use the assumption 1 and assumption 2, and then from there, what kind of scaling law we can get. Okay? So here's the correlation function at some position R. Now it's defined on the cross-grained system. So I'll use RL and TL to represent the correlation functions. So the definition is that now you are studying the block spins sitting at site I and site J. And the definition of correlation function is just like the definition of the usual spin model. Okay. So as we already mentioned, that we know how the effective Hamiltonian HL is related to the original model, which is defined with lattice constant L. So I'll just reproduce it here, times LD. Okay. So as we also postulated, by the way, I forgot to mention another thing. So here this RL is basically the distance measured by LA. So what do I mean by that is the distance between I and J. Is actually RL times the length unit LA. Okay. And of course, we assume that at this moment, RL is much larger than A. L is much larger than A. So we don't need to worry about the microscopic lattice length. Okay. So anyway, so let's get back to what HL is doing. So we know how the model before we do the block spin transformation and the model after we do the block spin transformation, the effective field is related by this equation. But we also have the assumption too that this HL must be equal to H times L to the power of YH. Okay, with YH greater than 0. So from here, we can try to derive what ML bar is. So basically, because H are the same, so we can just drop it. So as a function of L, ML bar will be basically HL divided by H times L to the minus D. And because we know HL is H times L to the YH, so this thing is basically L to the YH minus D. Okay? So this is just, try to shuffle things around and you implement the assumption that HL is equal to H times Y to the H times L to the YH power. Okay. Anyway, so that's how ML bar changes as we do this block spin transformation. So now we can try to look at the Green's function or the correlation function again. So correlation function, I'll just write it down again here. Basically, Si, Sj, subtract Si, and Sj. Okay. And let's remind ourselves what Si is. So Si is basically 1 over ML bar, absolute value, times L to the power of D, and sum over all the spins within this block spin I. Okay? So this is the information that we're going to use to plug that into the correlation function. So once you do that, what you'll get is the following expression. You will have ML bar square and LD, basically 2D, and you will have summation. I belongs to the block spin block spin I, and the little j belongs to the capital J block spin, and you will have Si, Sj, minus Si Sj. Okay, so this step is not something non-trivial. You just plug that into your correlation function. Okay, and the good thing is that now you know how ML bar transform as you do the block spin transformation. So you can replace this term by some power of L. So eventually, what you are getting is it would the prefactor would just be something related to L. I'll just write it down a bit later. But there's another thing which is related to the Green's function of this part. Because if you just stare at this, this means that you are trying to calculate the spins correlation function between the I spin and J spin. So little I and little j. So what do we mean by that? So basically you have a block spin centered at I, and you have another block spin centered at j, right? And I spin is somewhere here within the I block, and j spin is somewhere here within the j block. And you are trying to calculate the correlation, basically this thing is basically the correlation function between these 2 points, right? And you are summing over all these possibilities, which means that you have a bunch of I and j, so maybe you are calculating the correlation function between these two, or maybe correlation function between these two, or correlation function between these two, something like that, okay? And the argument is that this distance is much larger than the length scale L, which means that on average, to some extent, you are summing over a lot of these functions, but these functions are more or less equal with each other, okay? But how many terms are there? There will be LD terms here, and there will be LD terms here. So there are totally L2D to the power of 2D terms there, okay? So here is the approximation that we assume that this RL is much larger than L. So what we got is, just let me write down everything. So ML bar is related to this L to the YH minus D. So I will have L to the 2YH minus 2D here. Okay. Wait a second. Is it correct? Yeah, I think it is correct. Okay. And we will have L to the D and L to the D times Si and Sj. Okay. Wait a second. No, I think I made some mistake. This is, sorry. This is this, so I should have L to the 2YH minus D. That's the 1 over ML bar square. And I still have this L2D here. Okay. So now, if I collect those powers of L correctly, this will be cancelled. So eventually I got L to the 2D minus YH times the Green's function defined by the original lattice model. Okay. So what I'm doing here is basically I build a relation between the cross-grained correlation function and the correlation function before we do the block spin transformation. And they are related by how you do the block spin transformation in this way. Okay. So this is nice because in the sense that we should be able to build some kind of scaling relation between the models. So let's see how to do that. So we have some Green's function or some correlation function defined by temperature TL and some magnetic field HL, and the distance or the distance that is measured at the length using the length scale of LA is basically the real distance or the physical or dimensionless distance divided by L. And it must be equal to, according to this relation, L to the 2D minus YH times the correlation function, but now it is defined on the original lattice with lattice space in A, so we'll just use R to represent it, and at a certain temperature T, and certain reduced effective field H. Okay. So how we get this power is by inserting the fact that we know how ML and we know how HL and H is related, and we assume that H had this particular power law form assumed by the second assumption of Kadanoff. Okay. So now we can also try to insert the assumptions by Kadanoff here. So I think let me see what's the assumptions form to make sure that I have the right definition. Basically, TL is replacing by this, and HL is replacing by HLYH. Okay. So basically that's the relation, and as we mentioned, we can arbitrarily choose L, but we can follow the previous convention that we choose L such that TL to the power of YT is equal to 1. That basically effectively says that we can replace L everywhere by T to the power of minus 1 divided by YT. Okay, so if it is so, we just plug that back, and eventually what you are getting is G of R times T to the power of 1 over YT. And now because we choose T times LYT to be 1, so this is 1. And we have H to the power of minus, YH divided by YT. And this is equal to, wait a second, I still need to deal with the other factors. And it will be equal to G, R, and TH. Okay, so basically it is completely identical trick that we used previously. So all right, so once we have that, eventually we can define this object to be this scene. Oops. This is just a definition such that we can see the function form directly. Okay, so if you do that definition, what you are going to get is your correlation function as a function of R, T, and H will look like this. Okay. So this will directly suggest the critical exponent mu, which is something that's related to your correlation function, will be 1 over yt. And this power to d minus yh will basically be equal to d minus 2 plus eta. And still you have the delta equal to yh divided by yt. And this thing is something that we didn't prove at this during today's lecture, but it is related to the scaling form that is related to the third and the fourth relation between the scaling hypothesis that I didn't mention, but you can try to show that. But anyway, the point is that similar arguments, but if you apply to the Green's function or the correlation function, you can see there are some relation between the critical exponents, and they are all reparameterized by this postulated critical exponent yh and yt. Okay. So that's basically a good point to stop and think about what we have done. So basically what we are trying to say is that Kadanoff's trick basically relies on two assumptions. One, the Hamiltonian, after you do the block spin transformation, basically did not change its form, okay? So that your Hamiltonian still looks similar, and because the form of the Hamiltonian is the same, the singular part of your free energy should also have the same form. So all you need to do is to change the corresponding, reduce the temperature and reduce the effective field H. Okay, that's a very strong assumption one. And then the second assumption is, if we only have assumption one, then basically we are stuck because we don't know how this reduced temperature and reduce the field transform as a function of the L, which is how you do the block spin transformation. So we very boldly, or like a Kadanoff very boldly, assume that since we are looking for something related to scaling behavior, why not just postulate that these parameters, reduce temperature TL and reduce magnetic field HL, has some power law dependence or scaling law dependence on this block spin length scale L. Okay? So once you make this assumption, it turns out that you are actually reparameterize your critical exponents, basically this alpha, beta, gamma, and delta, using two different exponents, yt and yh. So at this moment, we are doing nothing. We are just saying that the original scaling problem is equivalent to finding out this value of yt and yh using the Kadanoff's idea. Okay? So that's the two assumptions. But here I will just try to give you some a reminder that assumption one is actually quite dangerous. Or the form of your Hamiltonian should be the same after you do the block spin transformation. Basically, it's not true in general. Okay, why it is so? Let's consider a model that has further neighbor hopping. Further neighbor interaction. So at this moment, we only consider the interaction between the nearest neighbors, right? So if we consider the next nearest neighbor, not the next nearest neighbor, like if we consider the further neighbor interaction as if like these red bonds, okay? So what is going to happen is that if you insist that the format of the block spin transformation should be the same, give you the same Hamiltonian, you'll get a quite unreasonable assumption because at this moment, before you do the block spin transformation, this spin can couple to this one and couple to this one. But these two spins are basically the nearest neighbor for this block spin, okay? So it doesn't make sense if you require the form to be the same. It means that you need to have this spin directly coupled with the spins at the next nearest neighbor block. But from the microscopic model, this process doesn't exist. Okay, so this assumption one in general is not true, but as a to develop the idea, we still take this relatively restricted idea and try to see what we can get. And later we will try to see if we really want to fix that, how we should fix it in an appropriate way. Okay. So what Kadanov's idea is more like give us a hint that there's some way along this line that worth us pursuing, but there are some problems. So in the next lecture, we'll basically focus on how to fix the Kadanov's assumption 1 and assumption 2 in a more precise or more generalizable way, such that we can really extend this idea and get the critical exponents or the idea of RG more specifically. Okay, so I think that will be today's lecture, and I'll try to post the lecture note of last week as soon as possible. And if you have any questions, you can just ask me. Okay, and I need to remind you again that please send me the proposed final presentation subject title and what do you want to do to me, so I can give you some feedback such that you are not, spending too much time on the final presentation or spend too little effort on how to do a final presentation. Okay, then that's it. And see you next week. Okay, so let's see how to stop recording.